Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to tackle the topic of surface area of revolution in parametric equations. It's a big, long title, and really we've made a natural progression up to this point, and let me review that now. We've talked about in regular functions, Cartesian functions, we've talked about the arc length, we've talked about that. Then we moved on and we talked about the surface area of a function that you rotate about the x-axis in Cartesian coordinates. Then we took a break and we talked about these things called parametric equations, which are just functions, and that circumference is 2 times pi times f of x. F of x is given by this thing right here. The length of the curve is already given to you from the previous section. You put those together, you integrate, and that's what we already talked about in the previous sections was the area. Okay. Now I'm going to write down the corresponding version in parametric equations without any proof at all, and we're going to look at why we think it's true. The surface area of revolution in parametric equations is the integral from alpha to bravo, so it's just the integral over the limits. Okay, let me write it down and we'll talk about it. 2 times pi times y. In this case, it's y of t, just because we're talking about them. Okay, so the first problem is going to be x is equal to 1/2 t squared, and y is going to be equal to t, and the parameter t is only going to vary from square root of 3 all the way up to 2 times the square root of 2. So it's a kind of some wacky limits, but that's the way they are. It goes from square root of 3 up to 2 times the square root of 2. This is my function defined in terms of parametric equations because t is my parameter, time basically. So 1 and dy dt squared is 1. So let's go ahead and put them into the relation for the area and see what we get. We're integrating from alpha to bravo, which is square root of 3 to 2 square root of 2. So it's square root of 3 to 2 times the square root of 2. We're integrating that. And what we're integrating is 2 times pi times y. Y is my function, so it's just t, times the square root. Dx dt squared is t squared plus dy dt squared is 1 dt. Okay? dt. Of sine is cosine of t. And then we're going to take dy dt squared, because we know we're going to need that in the problem. Squaring this is going to give us exactly the same thing. 4 times the sine squared of t times cosine squared of t. Okay. Now what we're going to do now that we have all the information is we're going to plug it in to our formula, which is integration from alpha to bravo, 2 times pi times y times the square root of dx dt. Happy when you see something like that. You're probably on the right track. Integral 0 to pi by 2, 2 pi times the sine squared of t. I haven't done anything but rewrite this stuff. This is going to be square root of 8 is going to be, let me go ahead and put some parentheses around this. It's going to be 2 times the square root of 2. That's what we just found out. Square root of 8 is 2 times square root of 2 times square root of sine squared is sine of t, and the square root of cosine squared is cosine of t, dt. Okay, so I still have to integrate it, okay, but I got rid of the radical. Can you substitute u is equal to sine? Well, you could do that. You would take the derivative and cancel with the cosine, but that doesn't really leave you with that much, okay? There's a lot of ways to probably do this thing, but the way I like to do it and the way I did it is what you can do is you can rewrite this sine as 1 minus cosine. So it's going to be 4 pi times the square root of 2. And basically what we're going to do is we're going to apply one of our tricks back from 3 or 4 or 5 sections ago on the trigonometric integrals. We're going to apply one of our tricks. This integral is going to be 0 to pi over 2. I'm going to 1 over sine t du. That's what I did there, and that's exactly why I did it, because this sine cancels with this sine. Now I have an integral only in terms of u. Okay, only in terms of u. So let's simplify this stuff. 4 pi square root of 2, okay, integral from 0 to pi over 2. Now let's distribute this stuff in, okay? Don't forget you have a negative here, okay? So what you're going to have is u times 1 is u minus u squared times u is u to the third power, and you're going to have times minus 1 du, okay? So what I'm going to do next is I'm just going to do a little bit of rewriting. I'm going to take this guy out. I'm going to say negative 4 pi square root of 2 integral 0 to pi by 2 of u minus u cubed du. u. We just took the negative out. That's all I did. Now, this is really easy to integrate. This is just a polynomial, so it's negative 4 pi square root of 2 times integral of this is 1/2 revolution, the area of it, and actually I put an L there, that should be A because this is the area of a surface of revolution, is integrating from the limits 2 times pi times y, which gives us that circumference, times the length as defined in the parametric equation. Okay, so 2 times pi times y, which was sine squared of t, and then we put everything that we knew under the integral, the squares of the derivatives, and then it turns out we could actually take the square root of this, which is nice because that radical goes away. The 8 gives us 2 square root of 2, and the squares just disappear from this other stuff here. We got down to this point if it's defined parametrically, which just means that its coordinates are dependent upon some third parameter, usually t for time, and they're independently described by that variable there.